Okay, in this tutorial, we're going to talk about the different ways that continuous variables can be represented in the data visualization here. Now, when I say continuous variable, I mean one of these quantities that we measure with our scientific instruments. So thickness, color, roughness, and gloss. Um, Technically, year is also a continuous variable, but I'm going to focus on these measured quantities. Now, right when you open the app, one of these variables is already represented, and that's color. And actually, here it's not represented as a single variable, but as this what you would probably call a three-dimensional variable, um, which is visible color, right? So the base color of the paper sample is already mapped to the color of these items, and if we zoom in, we can see this a little better. You see they're all slightly differently colored. And this grid is actually organized by base color, or at least one dimension of the base color, which is the warmth. And that's the primary axis along which these colors vary. But since we had to choose like an RGB color to assign to each one of these blocks, it's actually three-dimensional, R, G, and B. But the idea here is that for our purposes, color is typically a single variable, which is warmth. And so the very cool colors are down here, and the warm colors are up here, and they're sorted like that. So right away, we already have the representation of a continuous variable. But there's a lot of different ways that you could look at this, too. So, for example, right now we're just in a grid, and a grid is useful because it's ordered according to color. But one thing we can't see very easily yet is the exact distribution of those colors. And in order to see a distribution, you look at a histogram. So let's click the histogram. Okay. Now it's much more clear, right? We can see that at the very cool end of the spectrum, there are some paper samples. But by far, the sort of largest color groups of these, or you might call them warmth groups, because we're not looking at all dimensions of color, but just warmth. The biggest groups are sort of in this low mid range, the higher mid range, and then we have a clump toward the high end. And then, like with most of these things, there's a long tail of fairly extreme values here too. But this makes it a lot easier to see. Technically, all the same information was present when we were in the grid, but it was a lot harder to see because it wasn't spatially organized in this particular way. And so here, each what you might call column. So a column is the vertical arrangement of these things, and then, the rows are the horizontal arrangements. But what we care about are the positions along this horizontal axis. And then if a bunch of items have the same position along this axis, they will just be stacked in a column. And the way they're stacked is we start toward the middle and we gradually add points on either side of the axis, forming this kind of over-under arrangement here, right? And we do that because it looks a little better. They're easier to see, and so on and so forth. But the idea here is that we kind of start in the middle and move outward, alternating between adding items to the bottom and the top. That's how these histograms are built. So that's what a histogram gives you. It tells you the distribution of a single variable. Now, normally, when you're looking at statistical charts and you look at a histogram, it's really almost kind of a form of bar chart. Okay, but in our case, these aren't actually bars. They're columns of these little visual marks, right? So this is a special kind of histogram that I call a unit histogram, right? Because each data point has a distinctive unit on the screen, right? And so rather than representing this histogram bin as a simple bar, we have represented it as a column of these little cubes, each one representing a paper sample. But what's nice about that is that then it's actually possible to sort those cubes vertically, okay? So we're looking at a histogram of base color. Here we go. And we could sort these vertical columns by some other variable. And in fact, they are sorted by another variable right now, thickness, because this menu, we've selected thickness. Now, you can't tell that yet, right? Because, well, how would you know that they're sorted? Well, one way is we can change the direction of the sorting. So right now they are ascending, and we can change them to descending. But these don't really look any different, right? Well, it's because the visual appearance of these cubes is entirely right now determined by their base color. See here, we've mapped the base color onto these cubes, and that's why, for example, when we're looking at the histogram of base color, and we look at one end, these appear to have the same color. The cubes appear to be the same color, and they're all bunched up at one end. These are the cool ones, and these are the warm ones. And when you look at the cubes, you can see that. These look cooler. They look a little blue, and these look a little yellow. And that's because we've mapped base color to the color of the object, in addition to having sorted them geometrically, spatially, by that same variable. But we can map other colors, right? Other variables to the color of these cubes. And so if we were interested in thickness, we could go in and we could map thickness values to these things. And since they're vertically sorted by thickness, they now look very kind of orderly, right? And so here, and just to remind ourselves of which colors are low and which colors are high, we can actually turn this into a thickness histogram. And what we see is, okay, the sort of purple are very low values, and as they get brighter into the yellow range, they're very high values. Okay, so now let's go back to base color. So what we're seeing here is actually two continuous variables mapped onto the same histogram. Now, it's important to remember, this is unusual for a histogram, as I said before. Normally, histograms are composed of bars, not these little individual units. And you wouldn't be able to do this coloring using another variable if they were bars, right? So in standard statistics, a histogram can only tell you about a single variable. But in a unit histogram, we can learn about two different variables at the same time. We're learning about the distribution of base color here, which is what the main histogram axis is. And then we've sorted these points vertically by their thickness. And in order to see that vertical sorting, we have colored them by thickness, right? Okay, so what do we see here? Well, remember that these purple values are very low thicknesses, right? So it turns out that as we move into sort of higher color ranges, we have like an interesting effect here. Some of the thinnest papers are actually higher color, right? Because this is the high end of the color histogram, and then we see these are the purpliest of the points. So that's sort of interesting. And we might think about how to explain that. But then let's change the direction of the sorting of thickness so we can see, okay, so what has happened is that items that don't have a thickness value here have bunched up toward the middle. So maybe we'll leave it this way. And so that those missing values are on the outside and not kind of getting in the way. But what we can see too is that some of the thickest values are also here toward the higher end of the color spectrum, right? So this is like mid-high color spectrum. You know, this is the low end over here. This is the very high end over here. We're at the kind of mid-high end here, but we see both the purpliest marks here and the yellowest, right? So we have both the kind of the thickest and the thinnest papers. And so that's interesting. And my guess is that what's happening is that older papers tend to have higher color, and most of the very thin papers in our data tend to be older. So that's probably part of what we're seeing. And then in general, when you have something that is a warmer color, apart from the effect of year, you're more likely to see like a thicker paper, right? Thick goes with warm, which goes with matte, which goes with rough. These are the sort of like expressive directions of each of these axes. And so you'll tend to see those correlated, right? But we have this kind of dual thing going on, which is kind of interesting. Now, you may know, if you know anything about statistical visualization, that when you typically want to see the relationship between two variables, you use a scatter plot. And so right here, we have been able to map two variables to this plot, but we might see it a little more cleanly if we put it into a scatter plot. And it's interesting to watch the transition from histogram, which we are now, to a scatter plot. So let's click and watch where the points go. Okay, that's interesting. Now let's go back and forth a little bit just so we can continue to see that transition. Watch, focus on a set of points and see where they move, right? It's not random movement, right? This is fairly ordered movement, and that's because this is all the same data in both cases, right? We're just seeing it in a slightly different visual layout. And so we should expect that, similar points will move together. Now, one thing we are seeing is that because the histogram has the kind of over-under arrangement, that these points under here have to make their way up here to join their other yellow companions here, right? And so you see that in the scatter plot. You see them all kind of bunch up together. And again, so we've colored these points by thickness, and we can see that now the y-axis is in fact thickness, and we can see that that makes sense. Okay, we have this kind of like gradient of color moving up. And so these are the low values and these are the high values. But what we can see here now is the relationship between color and thickness. And statistically speaking, not a very strong relationship, right? There's kind of points all over the place. One thing we can do is that this is a 2D scatter plot in a way, but we've used the third dimension for sort of stacking. So what can happen in a scatter plot is that you can have a very dense cluster of points, and then visually speaking, if you're just plotting them as points, they might kind of overplot each other a little bit, right? And then it gives you, it's harder to see that density because lots of points are sort of on top of each other. And so there's a lot of occlusion happening there. So what we've done here to get around that is that when points are occupying the same, coordinate positions here, they have roughly the same x and y values, then we will stack them on top of each other. And so if we hold down either command or the control key, we can rotate this visualization here. And so then now we can see, okay, yeah, there's a big sort of like tower of points here where there's a lot of density in our data. These are low color and low thickness points, right? These are very kind of less expressive papers. They're thin, they're very sort of like bright white, and there's like a lot of them here. And so that probably contributes a little bit to some correlation, right? Because there's a lot of probability density right in this one area, both low thickness and low color. That probably means that the Pearson correlation is not, close to zero, but there's also a lot of noise in this plot too, right? So in addition to having some very thin papers that are low color, like cool, we also have some very thin papers that are, if we look over here, we also have some very thin papers that are also much higher color. And then the sort of converse of that, we have some very thicker papers like up here that are nonetheless still very like low color. So there are a lot of like violations of this relationship, but we do see that there's a little bit of a relationship here, right? And we have these kind of middling color values and some middling thickness values where there's another sort of like dense cluster of points here. But now that we have two variables, and we can reset the camera by clicking that. Okay, so now all of our rotation and panning is now reset to the default. So we have thickness mapped to this y-axis, and we have color mapped to this axis, but we've still colored by thickness, and now it feels a little bit pointless, or redundant at least, to have thickness mapped both to this spatial axis and to the color of these points. So let's add another thing. Let's actually color the points by gloss. And now we have a third variable. So now we're actually looking at the relationship among three different variables, right? Because spatially we're organized by color and by thickness, and then the color of the points is determined by gloss. And so now you have to think pretty hard when you're trying to look at the relationships between three variables, right? It's like your eye might catch visually some patterns. So for example, very low values of gloss tend to be bunched up in the higher range of both thickness and color. And that is probably what you would expect, right? Because low values of gloss means matte, right? And matte papers tend to be thicker and they tend to be warmer. Or at least we've seen a weak effect like that in our data, right? And so we can see that play out here, right? So we also can see that the matte papers tend to be here. And then when we look at the very glossy papers, the very yellow colored squares here, we can see that the very glossy papers tend to be bright white and they tend to be thinner, right? So this big sort of cluster of these kind of less expressive papers here, we see also are very glossy, right? So we've seen those three relationships. By the way, when you start tilting the view, you can see in the distance there's this sort of like facade of points that is organized in the distance, right? The reason those points are there is that they do not have a thickness measurement. So because they're organized like sort of along the Y direction and they're moved, way out to the periphery, this means that they're missing a thickness measurement. However, because they nonetheless, so despite not having a thickness value, they do still appear to have color values. That's what gives them this shape, right? And it kind of matches the existing distribution. I mean, it's a little hard to tell from this, but you get this big kind of like peak around this area, right? And so this roughly matches the color distribution that we've already seen. And if we want to sort of like return to that, we could go back to the histogram and we can kind of like switch between these two views a little bit to kind of see that, right? You can, let me try and get a better view of that. So we can kind of switch between the histogram and the scatter plot. But you can see points are sort of stolen from the histogram and moved up here out of the way because they have no thickness value and so they cannot be placed along this axis. That's what those are. And then so you might think, well, equally, if they are missing a color value, they will appear over here despite having thickness values. And then if they're missing both, they appear in a column over here. So don't let those kind of distract you. The main event, so anytime you're looking at these scatter plots, you want to focus on the area where you still have axis labels here. So we can see, we have these values along the axis. If you stay roughly within this square, these are all the items that have measurements for both axes. Okay. Now, there is actually a third spatial dimension, as you can see. I mean, this is a 3D plot. So in fact, we could even add a z-axis to this, and then we would have all four dimensions, base color, thickness, gloss, and roughness, all in one plot. So let's add roughness. Okay, now we see some of these points have sort of come out of the plane toward us, right? And that's because they're now filling the z direction. And we can see if we rotate, we can see they've now all spread out. So now, in a way, this is our entire material space, represented using the colors of points and also three spatial axes. And we can see there's labels over here too. And then, if we want to think, very sort of deeply about where these points end up, well, what might we predict? We might predict that these very dark colored points, which are very matte, would tend to be rougher, for example. And we do see that. We see that if we look out at the sort of extreme ends of roughness, all of these points tend to be very matte, right? And then furthermore, when items are very smooth, they also tend to sort of bunch up when these other values are low, right? So smooth tend to be very thin. We can sort of see that here. We kind of move around this space, and so on and so forth, right? But, and this is certainly, these kinds of views, it's a little trickier to get, very precise estimates of the specific values in play here. But this is more useful as a way to start to understand the kind of shape of these distributions, right? I mean, because what you're basically looking at material space here. And one thing you might do to make this a little bit more sensible is we're able to map directly the base color onto these points. And so then if we switch this to gloss, now gloss, thickness, and roughness are mapped to the spatial dimensions, and then base color is mapped to the color of the points. And maybe that's a little easier to see because you can think that when you're looking at one of these squares, you're literally looking at the color of the paper. You're looking at the actual color of the paper rather than an abstract representation of the value. When we had mapped gloss to the color of those points, we had to do a little more cognitive work. We had to think, okay, when they're purple, that means that they're matte. And when they're yellow, that means that they're glossy. And that gets a little confusing, right? This is a little bit easier where all we have to think is, oh, these are like white and these are yellow, and that's what color they actually are, right? So this is probably the best way to see the continuous material space here, right? But we've come to learn that there are these different ways, 3 spatial directions and 1 color direction of representing these continuous values in the data. And so we might ask then the question like, well, what's the best way to see these things? And I wouldn't say there's any best way, but research about data visualization tends to say that it's much easier for the human eye to make sharp or precise distinctions if those distinctions are represented spatially rather than in terms of their color. So if you care very deeply, if the primary thing you're concerned with is, for example, base color, you probably want to map that to one of the spatial axes. So either you want it to be the primary axis of the histogram, the horizontal axis, and you can see its distribution, or you want it to be one of the axes in a scatter plot. And then if you have more of a kind of a secondary interest in some other variables, maybe then you would map those variables to the color of the items. Also, if you care a lot about the representation of a particular variable, you might redundantly map it to more than one feature of the visualization. You might map it to a spatial axis, and you might additionally map it to the color of these items. But in general, when you really care about something, you want to look at it spatially because you'll be able to sort of do the visual math better than if you're mapping it to the color of the object. But so here are some options to be able to do these things.